Chris and your colleagues, Elisa and others, thanks so much for running this seminar series. It's been fabulous, especially during the darkest of times. Excuse me, and the fact that it's continued is really great. I know I really enjoy tuning in every week. And I don't know how much of you caught Nicholas's talk last week, but that was fabulous. It's the quality of the talks, the lectures is pretty impressive. Hopefully this will live up to the quality. So I'm going to talk about give you an overview, sort of historical overview and present work that our team has done and is doing currently. There are many, there's a large cast of characters. This is only some of them that have been involved. But a special thanks to Chris Johnson, my close colleague at Los Alamos now, and also Bertrand and Claudia, who were there at the beginning of all of our work in this area, and Chris Marone as well, Robert Geyer, and others. Thanks so much to all of them. So I'll go ahead and move on, and let's talk a little bit about what we're trying to do. As everybody online knows, faults are incredibly complex. Even in the laboratory, they can be quite complex in systems where you're actually breaking new rock. And the question is, what can we do? What can we do that might add to what we're currently doing that could help us understand how faults work, sort of the physics of faulting? So that's really been our goal from the beginning. And before machine learning came along, I know I was very frustrated because we just weren't really making progress on this topic, at least in our lab. And I felt like things were kind of stalled, and the question was where to go with it. And that's when one of my colleagues suggested, what about machine learning? And my response was, what is that? This was probably in 2015 or so. And that was where it all started. He pushed me into going to a really interesting meeting in Santa Fe on machine learning in material science, where I met a couple of collaborators, including Bertrand and Claudia, their advisor. And that's where things got started. So how can we learn the controlling physics of such a complex system, and can new data analyses approaches help? So I want to give you a historical summary, as I mentioned. Then we'll talk about probing slowly slipping faults in Earth and stick slip in Earth, current work, and then conclude. So this is a slide I like to show just to get a sense of, well, the basic question in regards to the data we're using, the primary data set. And that is, we all know that we all use the different phases of a wave, compressional wave, shear wave, surface waves, etc., for imaging, for characterizing the source, etc., etc. But the question we were asking at the beginning was there information contained preceding the compressional wave and following the surface wave that might be useful, that might be telling us something about the behavior of the fault? So that was really the point of departure. So here's the famous BIAX. Since Chris and I have collaborated together for years, we were using the BIAX data. I think everybody online probably is familiar with it. You put that central block downward. In general, a constant displacement rate. You have gouge layers on either side. This is held in place with a normal load. And you get, as you come up to steady state as a function of time, the shear stress or the friction, you have an increase in these quantities, and then you start to approach steady state, and eventually you get to steady state, which is what you see just above the cartoon of the BIAX itself on the left side. So the earliest and simplest approaches were based on decision tree models, and part of that was because they're simple, but also because you can back out the feature space to know what features are important and hopefully understand better how the model might be working and what might be important in terms of the guiding physics. So that was the first, these were the first models used. This was random force and exergy boost, and this was work spearheaded by Bertrand and Claudia, Nick Lovers, Kipton Barros, and others back in 2016 and 17. So at that time, and many of you are familiar with this, but if you're not, the input data set was acoustic emission recorded on the biax, and that strain signal is strain amplitude of the dynamic wave. So hopefully that doesn't confuse you. The label in this case was the shear stress or the friction on the fault. And so the question you're posing is there information contained in that window shaded by gray regarding the shear stress? Can you predict the shear stress from that window of the dynamic strain signal? And that's the question you're posing to the model. The model is f of x in this case. And here's going straight to the result. So you can see on the left-hand side the acoustic data again and the experimental runtime, and you're seeing the continuous acoustic emission. You can see the bursts of sound associated with each stick slip event. And that very small blue window, you can see with an arrow going over to the right-hand side, is trying to predict that shear stress at that instant in time.
Am I the only one? I think I'm not seeing the next slide that you're talking about.
Yeah, I was waiting.
Same here.
Yes. Oh, yeah.
How about now? Can you see it now?
Yes.
Yeah, no, I see it.
Okay. Thanks for interrupting. I really appreciate it. And if that happens again, please do interrupt me again. So just quickly again, the left-hand side is the continuous acoustic emission. That tiny blue window, in that window you're asking the model to predict the shear stress shown by the arrow on the right-hand figure. And so if you run a moving window analysis through the time series and try to do this at each instant in time, it could be an overlapping window or not. You're posing this question and asking the model to tell you what the current shear stress of the system is. And indeed, the blue curve is exactly that. The blue curve is the shear stress of the system as a function of experimental runtime. And the red curve is the ground truth, measured directly on the apparatus, on the biax apparatus. So you can see it does a pretty good job. And this was a huge surprise because what it told us was that there was information contained at all times in the acoustic emission signal coming out of the biax regarding the state of the fault. And we had no idea this was the case. You know, we knew there were impulsive precursors preceding failure, things like that, but we didn't realize at that time there was information at all times that could tell you about the instantaneous shear stress, the friction, and it turns out you can build a model for the gouge thickness, the displacement, and other quantities. So this was one of those aha moments one has in science that are pretty rare and put us off in this direction where we're still going in. So I'll move on. So you could also predict time to failure using the same approach. So in this case, you're asking the model to tell you how much time is there left before the next failure event. So you're not actually looking into the future. You're simply trying to predict that curve. You see that red curve on the bottom. Can you see that, by the way, Chris?
Yes. Yes.
Great. So you're predicting the instantaneous time to failure. So it's not really a future prediction, but it's pointing toward the failure time, if that makes sense. And let me show you how that worked. And that failure time is strictly based on the shear stress signal you're seeing at the top there. So you're just making this sawtooth signal based on the time to failure using the shear stress signal. And here you see the prediction and the ground truth again. The red dashed line is the same red dashed line you see in A.
Okay, now we're
okay. How's that?
Now we see A and D.
Good. Okay. Thank you. I really appreciate it and apologize for this. So again, the red dashed line is the same one you see in A, and the blue is the prediction, the instantaneous prediction. So you can see at any given time, it does a pretty good job pointing to the next failure time. So you can get a pretty good idea of time to failure. Much better than you would, for example, taking the average or some other statistic metric of the inter-event time. And here you should see a B, I hope, and if not, speak up. But you see the strain signal at top, the dynamic strain signal.
Not
Then you
yet.
see, okay, then you,
Maybe just advance the slides a few seconds before you're planning to talk about it.
okay, do you see B yet?
No.
Not yet.
How
There
about
it goes.
now?
Oh, yeah.
Yep, yep. Yep.
Okay, do you still see it?
Yep.
Okay. I don't know what's going on, but we'll just have to put up with it, I guess. So that there's the dynamic strain signal again on the top right in B, and then you can see three of the most important features that came out of that work that allowed the predictions of both the instantaneous displacement and the time to failure. So it turns out the energy statistics, such as variance, kurtosis, and thresholds, were the most important. There were about 6 or 8 of the most important features, and all of them were energy related. So it was telling us that there was something being broadcast in the acoustic emission that was energy related, probably kinetic energy related, that was evolving through the stress cycle, and it allowed the model to give you the information it was giving you in terms of the questions we were posing: instantaneous displacement, friction, or time to failure. So that was really satisfying, because this didn't seem like black magic. It seemed obvious. And had we just been looking at variance, kurtosis, and thresholds, we would have seen this right away. We would have known there was information contained in the signal at all time, but we hadn't done that previously. So this is one of the many things this sort of model was teaching us at the time. So now I'm going to move on to a very brief discussion of episodic slow slip and tremor Cascadia and what we're trying to do there. Work spearheaded again by Bertrand and Claudia. And so I'm showing a map right now, Vancouver Island. Anybody see that?
Yes, that's good, Paul.
Great. Thanks, Chris. So in this case, you're using continuous seismic emission from a seismic station on the surface in Cascadia, on Vancouver Island. And the model output or target or label is GPS displacement rate as measured on the Earth's surface. Models again were XGBoost and also using deep learning models such as an autoencoder. That was the primary deep learning model that was being used at the time. So you're trying to do exactly the same thing we were doing in the laboratory, now on much larger scale, and this was for slow slip. And the reason we were looking at slow slip was because, as many of you know, there are many slip events that have been recorded since the early 90s when there was good instrumentation in this region. So we had quite a large number of events for training and testing. Those events take place on about a 13 or 14 month cycle. So we had a sufficient number, as it turns out, to train and test on. So I'm going straight to the result because I want to get on with the newer things. This is all older work. So this is displacement rate. I hope you can see the figure, and if not, please speak up.
We don't, Paul. We're still on the map. Now we do.
Okay. So this is the red line is the GPS signal as measured on the. For those of you that know these stations on Vancouver Island, and the blue is the predicted value. There's a region in there where there was missing data, that crosshatched region. But you can see that the prediction, using again a moving window analysis, the prediction is quite good, or was quite good regarding, if you take a mean with your eye of the GPS displacement rate, it looks as if the model is calculating that quite well. So that was very satisfying, because it meant that we could take what we learned in the laboratory and apply it to field study. There was still the burning question about stick, slip, and earth, and we're going to get there. But it's a question of training and testing for supervised learning. So in any case, I'm going to move on now. And the problem we have now is the long repeat time, right? We're all familiar with this. How do you deal with repeat times that are 30 years to 1,000 years roughly? So we don't have data to train and test on. So we can't apply the same approaches we were applying in the laboratory and in Cascadia for slow slip. At least in general, we can't. And I'll show you an instance where we can. So this took a lot of head scratching and discussions amongst us to try to understand how to approach this problem. And I'm going to walk you through the approaches that we have developed or are developing currently. So, let's see. I hope you see now the slide of Parkfield. So the first thing that Chris did when he came as a postdoc to Los Alamos was to attempt to apply this general approach to seismogenic faults, well, to the Parkfield section of the San Andreas Fault and also the Hayward Fault. And it didn't work. And we believe that it was primarily due to the noise levels relative to the signal levels at Parkfield, although clearly it could have been something else. Perhaps the fault's not emitting this signal. We don't know. But we believe it was because of the noise based on all the other work that we've done and are currently doing. So it's really back to the laboratory and fault simulation, and I'm going to get there in just a moment. But just over a year ago, Paul Siegel presented a really interesting talk on the 2018 collapse event at Kilauea. And so at that point, we decided to try to get hold of those data from Paul and others and tackle that problem. And that's what I'm going to describe next before we get back to simulation and other laboratory studies to develop the approaches we would apply to seismogenic faults. So you should currently see the slide related to Kilauea. There should be a map in the bottom right-hand corner of the caldera. And I'm only going to show this one slide. I'm not going to show the model or anything else. If you have questions about that, you can ask or get in touch with us. But this was also a decision tree approach. What you see here in the top figure in A, if you're seeing that, is the displacement as a function of calendar time. The ground truth is the red again, and this is GNSS measured on the ground, and the blue is the prediction from the model. And you can see in the zoom in the bottom left that it does a pretty good job. It's not perfect, but nonetheless, it does a pretty good job. And there's a lot one could discuss about the details here, but I think the satisfying part was it seemed that the same general approach could work for seismogenic faults that are modest magnitude, 4.7 to 5.4 in Earth. So we've scaled up markedly from the laboratory. So this was a really interesting exercise and again, very satisfying to tell us that at least we seem to be going in the right direction. So now I'm going to move on and come back to, as I promised, simulation and laboratory as we develop other approaches to tackle seismogenic faults in Earth. So here are three of the approaches we're taking. One is, okay, since we can't train on earthquake faults in Earth because we have insufficient data, except in instances like Kilauea, let's train on Earth fault simulations and test on laboratory and ultimately actual faults. So that's the first thing I'm going to show you.
And Paul, we're still on the Kilauea slide, and now we're okay. Yep.
Okay. All right, I'm forgetting to go ahead and then come back. So thanks for keeping me honest, Chris. So number one is to train on Earth fault simulations and test on laboratory or actual faults. And I'm going to show you results where we're doing this with simulations in the laboratory. The second approach is to cross-train the models with an eye on Earth, and I'll describe what that means when I get to it. And then we're also using informed machine learning, which is fairly new in the machine learning world, and looking to be extremely powerful, where you include a deep learning model and also a physical equation. For example, rate state friction. So let's walk through a couple examples here. So you should see a fault simulation in this figure. And this is in the upper left-hand corner, this is using something called HOS, Hybrid Optimization Software Suite, which is finite difference plus finite element method. And so these were simulations done by a postdoc in our group, really for a different shear apparatus, the photoelastic shear apparatus that we had up and running at Los Alamos, run by Bob Ecke. Some of you know Bob. And so it wasn't even geared toward the biax. You can see we have a single layer and we're shearing one layer and holding the other layer fixed. The material properties are very different than they are in the biax, etc. So we thought this isn't going to work, but let's try it anyway. So here's the simulation data. I hope you can see. So you should see in the bottom figure the friction coefficient as a function of time from simulation, which is the black curve. That's the right-hand y-axis. And the left-hand y-axis is the average velocity of the bead pack as measured by the bead pack in the simulation. The upper and lower plate are the blue and the red successively or respectively. And so we're measuring the velocity, average velocity on both sides of the plate. So these are the data. The input data are going to be the velocity, average velocity signal. Excuse me, it's going to be, I'll take that back. It's going to be kinetic energy. I'm going to show you that in just a moment. And the label is going to be the friction coefficient. So we're doing the same thing now, right? We're doing the same thing as we've done before, but now we're using a proxy for the acoustic emission, and we're trying to predict the instantaneous friction coefficient. And we do this. I'm just going to show a little bit of detail about the approach for those of you that are interested. This is an encoder and decoder trained by, so the approach is an encoder and decoder model, where you're altering the latent space for certain aspects that I'll get to. So I guess I won't say more about the model because unless I have that in the next slide. I do have it in the next slide, and I'll show that to you, those that are interested, very briefly. So you should see the encoder decoder model just for those of you that are interested. You're using scalograms in this case. These are details that are not important for most of you. You're downsampling through four separate layers. There are skip connections. It takes you to the latent space, and then you upsample back to the output scalograms. So I'll leave it at that unless there are questions and move on to the results. Hopefully you're seeing the results here of simulation on the left, and maybe you're seeing the laboratory on the right. And what you see here is that on the left upper panel, you see the kinetic energy as a function of experimental runtime.
We only see the simulation, but we don't see
you don't see the laboratory. Thank you, Marion. So that's what you should be looking at then, is the simulation. So that topic energy, of course, is positive in any case. And then so you're using the data on top as a proxy for the acoustic emission. So it doesn't have attenuation, but it does have everything else except site response, you could say. So it is a proxy. And remember, this is again a simulation for something that's very different than the biax. But so in the next figure, on the right-hand side, which I hope you see is the laboratory result.
Yeah, we see it.
Okay. So the laboratory, you're seeing the normalized acoustic emission in the top panel and the friction coefficient in the bottom. And so the first step you're trying to make is, can you predict the friction coefficient in the finite element, discrete element simulation? Then can you use transfer learning and predict the friction coefficient from the laboratory experiment using only the simulation kinetic energy data? So these are the two steps you're trying to take, and now I'm going to show you the results. I hope you see the results of the cross-training model. There should be at least one panel called A, and possibly B and C are showing up as well. Do you see A? You see it all? Good. So in the top panel, you're training and testing only on laboratory data, just as a baseline measurement. So you're using the same model to train using the acoustic emission and predict the instantaneous friction on the fault. Then in the middle panel, B, you're training only on simulations and testing on laboratory data. And so you can see it's much, much poorer than using the slip events. It's capturing the curvature of the stress of the friction drop, or frictional failure. But nonetheless, it's capturing characteristics that are truly surprising, because again, the simulation was for an experiment that was very, very different than the biax. So there was clearly something in the statistics of the simulation that is capturing the statistical behavior of the acoustic emissions in the experiment. That's the way we are interpreting it. The fact that it worked at all. So this was a big surprise, but gave us hope about, future simulations in Earth. So then in C, what we did was train the model using only the simulation and trying to predict the laboratory friction. Then we retrained just the latent space using several cycles of data from the experiment. And again, this is with an eye on Earth, where you have really limited data. So you're training on simulations, then you retrain the latent space with several cycles, and you see what you get. And you're seeing that in C. So you can see you're not doing as well as you are with training on the laboratory acoustic emission, but you're doing pretty well. You're missing the full frictional failure again, but you're capturing a lot of the details of the evolution of the signal through time, frictional signal through time. So this was pretty satisfying to know that this could work. Now, the one issue here is that we use several cycles from the laboratory experiment, which we don't have in Earth generally, right? We have a portion of a cycle in Earth. So let's look at doing something similar with this data set. So you should see a cross-trained model with a small portion of laboratory data now. And what you should see is in the top, let me make sure it's there. Okay, so in the top, you should see the normalized acoustic emission as a function of time, which is the red signal, and then the friction coefficient is the blue signal. So this is laboratory data, and that was the acoustic emission, by the way, is normalized. Again, I just want to make that clear so it's not confusing. And you're going to retrain that latent space with either post-failure or pre-failure and compare. So you have something like a third to a half of the stress cycle or frictional cycle, and you're going to use the data from that to retrain the latent space. And if that's confusing, please stop me and I'll try to explain it in a better way. But in any case, so in the bottom, you should see that the model trained by pre-failure and trained by post-failure. Focus your attention to post-failure.
Oh, we don't see the bottom.
You can see that by retraining the latent space just with the post-failure data, you do a decent job. Again, you're not capturing. Yes.
We don't see the bottom. We just see we're still. Not yet. There we go. No, it keeps showing up and then going away.
How's that?
Still don't see the bottom.
How about that?
Yep, now we do.
Okay, so you can see it does, an okay job. Again, it's far from perfect, but considering all of the sort of shortcuts we took, starting with using a simulation that wasn't appropriate necessarily for the biax data, it works pretty well and gives us hope that using simulation and some portion of an earthquake cycle and Earth data to retrain the latent space we have a chance at success in Earth. So that's a large stretch. I know those of you who do fault simulation would surely agree with me, but that's where that body of work is headed. So I'm going to move on to the prediction question, okay? And so now you should see a picture of Benno Gutenberg on the right-hand side of this slide, and a message from Mr. Herman Saylor. Dear sir, this laboratory does not predict earthquakes. Specific predictions giving time and place come from amateurs, publicity seekers, believers in the occult, or just plain fools. Los Angeles remains exposed to the risk of a great earthquake, which may take place at any time. So I don't know who I lifted this from. It was either off the web or maybe it was from John Badali, who's listening today. I can't recall, but it's just so amusing. And you know, we know it's a stretch, right? Prediction of magnitude and timing and location is a really heavy lift, but that doesn't mean we quit trying. So we're continuing to work in this direction as well while we're working on just the fault physics.
It wasn't me, but I just took a screen grab. Very nice.
Okay, so I can't remember who I got it from, but in any case, maybe it was Thornley. So let me continue. So now, so this is work in progress, additional work in progress, approaches to seismogenic faults in Earth. So one of the things that Chris and I, Con Wang, Kane Bennett, a small group of us started working on about a year and a half or 2 years ago was to try to predict near-term instantaneous characteristics of the fault system, again with an eye on Earth ultimately, but starting in the laboratory. So the idea is it's like it's using approaches very similar to what is on your iPhone or whatever phone you have, where when this annoying habit and sometimes useful habit of the phone where you're typing something in and it's giving you a word, either the correct one or incorrect one. These are natural language processing algorithms. And so they have their faults, but they can also be very useful. So conceptually, this is what we're using as well. And the idea here is that you're taking a portion of the acoustic emission associated with a certain friction on the fault or shear stress, and you're trying to predict just slightly into the future to see how well you might do. So that's what I'm going to show you next. I'm going to skip that one. I thought I was going to show you that next, but in fact, I'm going to digress for a moment if I could. Please humor me. I hope you can see this slide of Chat GPT. Can you see that?
Yes, we do.
Okay. So many of you are aware of Chat. It's gotten so much buzz when it was released in November for beta testing. And the reason I'm showing you is because of the impact I think it's going to have on all of us and our scientific work as time goes by. So Chat GPT is not the only algorithm out there, but I can just show you a couple examples of how remarkable it is, but how also it fails as well currently, but it's going to get far better. So I have a question here about, tell me about Chris Marone and his work on earthquake faults. So I input that into Chat GPT, and what it comes up with, I hope you see, is that Chris Marone is a geophysicist and professor at Penn State University, et cetera, et cetera. So it scrubbed the web for information about Chris, and it's actually, it's quite accurate regarding, you know, what Chris has done and what he works on. It's not very detailed, but it could be much more detailed if I'd asked for more detail. So this was, you know, 5 seconds later after I posed the question. So, you know, this of course you can use to, people are using to write papers, people are using to write proposals, et cetera, because you can put this kind of information in, and rather doing a Google search and doing all the hard work yourself, Chat GPT gives you the result. Now, So the next question I asked was, what are transformer models in machine learning and how are they implemented? Hopefully you see 24 seconds later the result. I'm not going to read this whole thing, but transformer models are a type of neural network architecture used in natural language processing, et cetera, et cetera. So then I asked it, okay, can you write a natural language processing code from scratch for me to predict text placement? So indeed, 20 or 30 seconds later, it produces a code to do exactly that. And I hope you can see it. And so I think the very remarkable and amusing thing is you don't even have to write your own codes, but you can check them for how well they're working, right? And you can check to make sure that you believe and agree, but it's a great learning tool as well. So I just wanted to digress and do that. And this means that outfits like Google are pretty concerned, because now you don't necessarily have to do a Google search. You can just put in Chat GPT and pose a question and it does it for you. So we will be using the same kind of approaches ourselves to build models, to apply to basic questions of physics. When you have a question, some sort of question in physics you want to ask, rather than going to Wikipedia, you might just put this into Chat GPT and you get the result. So I think it's going to, as I say, have a fairly profound impact on us, and very rapidly. This is going to change how we do things. So anyway, I'll get off my soapbox and continue onward, okay? So now we're back to this immediate future earthquake prediction I mentioned using natural language processing. And again, what we're trying to do is take the acoustic emission from the experiment and predict the future friction on the fault, but the near future, not the distant future, although we tried to do both. So I don't know if you see the convolutional encoder decoder transformer model. I'm going to move on beyond that just for the sake of time and show you the result. So the immediate future earthquake prediction, you should see in this figure now. So the convolutional encoder decoder containing a transform model with attention heads, and I forgot to mention we're using attention heads as well for those of you interested in the model itself. We were using attention previously for instantaneous characteristics in collaboration with Hope Jasperson and Martin de Hoop at Rice, but now we're using the same general approach to predict the future behavior of the friction on the fault. So what you should see here is a scaled acoustic emission, absolute value from the laboratory experiment. And in the bottom, you should see the output friction as a function of experimental runtime. The black is the ground truth measured on the device, and the red is the future prediction. So you're predicting that just the near future from a certain instant in time, if that makes sense. And what we found is you could predict less than a second out into the future quite well. And as you got further and further in time, you did less and less well. But you could actually predict quite well the failure time as you approached failure. And that was very satisfying to know you could do that using this kind of approach. So, and maybe the most important aspect of the work. So we did a kind of a grid search to see how far out we could go. You couldn't predict very well beyond the next slip event, and you couldn't predict very well if you were at the beginning of a slip cycle. And if you're trying to predict the end of the slip cycle, the friction at the end of the slip cycle, you couldn't do very well either.
Paul, I think there's a plot we're missing, because we see the top, but we don't see any detail of the sort of stuff you're talking about.
Okay, so if you see B, the 4581 testing data, that's the plot I'm talking about.
Okay, yeah.
Okay. Okay.
And Paul, did you say
So
that
again,
the red curve in panel B?
Go
Did you already tell us the red curve in panel B, how many seconds out that is using to predict?
It doesn't tell you how far out. This was the optimal result for less than a second prediction into the future of the friction. And so you're not seeing that here. And I can point, actually, I may be able to go to, bear with me for a second. Let me see if I actually have the, yeah, here we go. I can show you this. So do you see a plot with pink background of many panels?
Yeah.
Okay, so this is for your sake, but those of you who might be interested, this is actually at failure time for the sequence of events in that experiment. And the black is the ground truth measured on the experiment. So you expanded this horizontally quite a lot, right? So very short interval of time at failure time. And the pink background shows you that the prediction is good using this short-term prediction, less than a second. The one without the pink background, the white one, is a failed prediction. But all the other events, and this is just the sequence A, B, C, D, E, etc., are the sequence of failure events from that experiment. So you can see it captured almost all of them, which was, again, pretty surprising and somewhat remarkable. So we were able to predict the near future behavior of the friction using the natural language processing approach. I hope that's clear and not confusing, but we can go, we'll have plenty of time for questions and we can go into that as you wish. So I'm going to then just go to my conclusions, the take-home message, which I hope you can see. And that is, so learning earthquake slip, the noise is the signal, is what we've discovered, and it's given us significant insight into fault physics, instantaneous displacement and future characteristics as well as friction, as well as the gouge thickness, as well as displacement on the fault, etc. It was thanks to machine learning tools, these revealed these characteristics to us and gave us this sort of insight. And machine learning is rapidly advancing, will have a dramatic influence on all of science. It already is. Things change so fast right now, it makes your head spin. It's hard to keep up with the literature and keep up with the most recent models. So that's all I have today. Thanks so much for your attention, and many apologies for this this phase delay I was having with the presentation.
This is fabulous, Paul. I'll invite everybody to unmute, turn your camera on if you want to or not. Let's thank Paul together before we start discussion.